Yeah, I have a mic. Yeah, okay, everyone can hear me. Okay, great. Hi, everybody. I'm Deborah Ferguson, and I'm really excited to get the chance today to tell you guys a little bit about numerical relativity and some of the challenges that it's going to face. So this is definitely a little bit of a shift from the earlier talks, but hopefully that's fine and everybody's down for that. So yeah, this visualization over here, by the way, is a visualization of the gravitational waves coming out of a numerical relativity simulation of the merger of two binary black holes, or two black holes, consistent with GW 190521, which was the first detection of an intermediate mass black hole. So just a little preview of what NR can do. All right, so like I said, I want to talk to you a little bit about numerical relativity. This isn't going to be in-depth in our talk, so I'm not going to go too much into detail here. Martin already gave a great introduction to it the other day, so just a couple quick words on the concept. So first off, we are just about at 20 years from the first successful simulations of binary black holes. Just realized that that's coming up in like a year, so that's really exciting. And I want to talk a little bit about what's happened over those 20 years and what challenges we're still going to face moving forward. So this plot here is another version of a similar plot that Martin showed. This is actually one of his. And it just wanted to reiterate that the area that we're concerned about here is when you have black holes that are of comparable mass to each other and we're wanting to actually see them merge. And that's when we really need numerical relativity. And you do this by computationally solving Einstein's equations using a 3+1 decomposition, where we take the beautiful four-dimensional space-time that Einstein gave us, and we break it back into 3 spatial dimensions and 1 time dimension, and it allows us to set up an initial state and evolve it through time to understand what these mergers of binary black holes will actually look like. And what's so exciting about this is that within this region, there is no missing physics for black holes in the vacuum case. Now, once you start adding in matter, of course, there's more complicated things, but for the black holes in vacuum, our only limitations here are computational in nature, in the fact that we are solving this on a computer instead of analytically. And this means that in this region, it is the most accurate method for studying such black holes. All right, so as we prepare for LISA, and as we prepare to do gravitational wave data analysis with LISA, we're going to require highly accurate waveform templates that cover the entire parameter space of black holes, as well as that cover the frequency band of the LISA noise curve. All right, so let's take that step by step, and first let's talk about the parameter space coverage aspect of it. All right, so here what I'm showing you is a plot that you can go read about in the LISA Waveform Working Group white paper, just quite a mouthful, but actually a lot of what I'm talking about today is straight from the numerical relativity section of that paper, so I would definitely recommend following up on this by reading that paper and looking at the citations therein, because you can get a lot more in-depth information if you do that. All right, so this is a subset of the numerical relativity coverage of public waveform catalogs. Specifically here, we're showing SXS, RIT, Maya, and BAM, and I'm only showing quasi-circular simulations in this case, not even dealing with eccentricity yet. So here, instead of showing the full spin-dimensional parameter space, we just have the mass ratio, the aligned spin, the spin component that's aligned with the orbital angular momentum, the perpendicular, and that's for the larger black hole and for the smaller black hole. And each dot in this plot is a numerical relativity simulation. So the very first thing that you might note is that it's very densely populated pretty much across this whole parameter space, below mass ratios 4 or so. And then above that, it drops off pretty dramatically. And for aligned spins, you'll still see some up to, mass ratio 10, couple up to a Q15. But for the perpendicular spins, the precessing components of the spins, there's extremely little coverage. And this is with already 5,700 waveforms that we have, roughly. So there's still a lot of work to be done, and there's still some definitely challenging regions of parameter space. So first, let's talk about that high mass ratio area of the parameter space. Most simulations have Q less than or equal to 8. I'd say most have even less than or equal to 4. There are a handful of simulations that go up to 128 out of the RIT group, as well as one that goes up to 1,024 for a head-on merger. So this is definitely something that people are tackling and are making progress on. This is actually another visualization that I did of a mass ratio 5 simulation as well. So this is something that we are, of course, working on. There are new methods that are being developed that should be able to go up to mass ratios from 100 up to 10,000. And so I'm very excited about the progress that's moving forward here. But it's challenging because it requires really high resolution to resolve the smaller black hole and the higher harmonics at higher frequencies, and it requires very specific gauge choices, which has to do with how we slice our space-time in order to do these evolutions. And you have to be very particular, and that can be quite challenging. Now, there are other methods that, rather than trying to push NR into these limits, maybe we can reach down or cover the whole space with models and things like that, and use numerical relativity to inform that and calibrate to it. And there's going to be a great poster on that that you guys should check out during the poster session tomorrow. Okay, now spin is also challenging, maybe a little less so, but most simulations have spins up to spins of about 0.9. Near maximal spins, the more nines you want trailing that decimal, the more challenging this is going to get. They require extremely high resolution, similar problem to what we have with the high mass ratio, and it requires very particular initial data, and that can be challenging as well as gauge choices once again. There are definitely successful simulations out of SXS, out of RIT. Go find those papers. Sorry, do not be upset if I miss a citation to a paper. You can't fit everything on a slide, but I do want to just highlight some of the things to give you some resources to go find. But even with these successful simulations, this is still a really large parameter space, especially once you include precession, because now you have 3 spin dimensions for each of your black holes. So it's a large parameter space that takes a lot of work to cover, and there are some really challenging aspects of it. And so I would also recommend Ryan Nowicki's poster, which deals with precession specifically relating to this. All right, and then earlier when I showed you that coverage of the parameter space, I was only doing quasi-circular simulations. Now when you add in eccentricity, you're actually adding in 2 new parameters if you consider the mean anomaly as well. And so that's introducing more dimensions to this parameter space to cover. Now it's really exciting that we have a reason to want to study eccentricity now, because most of the focus has been on quasi-circular, because that's what LIGO typically sees and what it would expect to see, given that eccentricity is one of the things that radiates away fastest and orbits tend to circularize by merger. But with LISA, we're going to be able to see a lot earlier in these orbits, and there's lots of other interactions that can cause residual eccentricity to still remain. So this is definitely something that we need to tackle, and like I said, it's exciting to have a reason to need to tackle it. But there are challenges associated with it. One of those, seemingly simple one, would be that there's no unique definition of eccentricity in general relativity. And so that poses challenges when you're trying to create eccentric models and when you're trying to get everyone on board and understanding of what their definition of eccentricity means, what your definition of eccentricity means, and if something in data analysis quotes, this is an eccentricity of 0.1, what does that actually mean? So that's something that we're working on tackling. And it also can be quite computationally expensive. If you want really high eccentricities, and in order to have multiple orbits, you're also going to need to be able to go out really far, and that creates computational challenges. As I already said, it also adds additional dimension, really 2, and that makes everything take longer and more effort. Now, there have been a lot of recent efforts to expand coverage of the eccentricity parameter space. I'll selflessly plug our own Maya catalog, which adds some contribution to the eccentric parameter space. RIT has also done that. SXS has been exploring this as well. There's going to be a nice talk by Peter James Nee on Friday talking about the impact of mean anomaly on the waveform and exploring that area of the parameter space. All right, so up to this point, I've still just been talking about black holes in a vacuum. And so now, once we start thinking astrophysically, we need to add matter back into our systems. And there are many, many different possible types of matter environments, including accretion disks, collapsing stars, dark matter environments. This visualization over here actually is from a nice paper by Jamie Bamber about a binary system merging within a potential dark matter overdensity. So this is, once again, something people are working on tackling. There are a number of GRMHD codes, and there's been a lot of progress in simulating such environments. And there have been a lot of talks already at this conference. I wish I could have told you to go to them. Hopefully you already did. As well as some new ones coming up, and a poster, and Manuela's plenary on Friday that will talk about the progress being made in these GRMHD. Oh, for anyone who doesn't know, general relativistic magnetohydrodynamics, so that's what GRMHD stands for. But yeah, so that's definitely something that there's progress being done on, but as we're talking about parameter space coverage, well, that adds so many possibilities that we're definitely going to have our hands full for the next 10 years simulating possible situations. Okay, so now we talked a little bit about matter, but I've still been in GR land. So now let's talk about beyond GR effects. And we had a nice talk by Nico Younes the other day about the fundamental things that we can learn from Lisa and how we can start probing GR. Here I just want to talk specifically about using numerical relativity for that. And one of the big things is that to really compare different models, like to compare GR to a beyond GR system, you would want to have template banks of numerical relativity waveforms in these various different theories. And so, yeah, that's what we're going to want to develop. This is challenging. Setting up the well-posedness of the initial value problem is difficult to establish in beyond GR. So typically, people separate out the beyond GR terms from a GR metric and then evolve them separately, and have been able to make significant progress in this. Over here, I show some work by graduate student Chloe Richards on the scalar hairs associated with axodilaton gravity. So this is definitely a thriving field that people are putting a lot of effort into. And then there's already work being done on extracting gravitational waves from such simulations. That's challenging, relating to what I was saying a second ago about this well-posedness of the initial value problem, but there's been a lot of progress. And so this is a successful direction that we are moving, and once that's fully ready to go, then we still need to create template banks. So, like I said, we're gonna have our hands full in the next 10 years, but job security, I think. All right, so that's about the parameter space coverage. Before we really dive into filling out the parameter space, we probably want to make sure that the waveforms that we're generating are actually good enough so that we're not wasting our time. So one of the first things relating to waveform quality is waveform length. And so with Lisa, we're going to be able to see signals that can be in band for months, years, yeah, insane amounts of times. And with that are going to be many, 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 many orbits instead of the handful of orbits that we tend to see in LIGO. And numerical relativity simulations are really computationally expensive. They can take anywhere between days to months to run. And the other thing, I'm going to talk about truncation errors here in a second, but they accumulate over the course of simulations. And so it doesn't become practical to create particularly long numerical relativity simulations beyond a certain number of orbits. But that's okay, because if you remember back to that earlier plot and the one that Martin showed as well, at large separations, there are other methods that are just as accurate or more accurate. And so that's great. We can hybridize with other methods, use numerical relativity for the merger, use other methods for the earlier things, create hybridized models, and be able to cover this entire, observe this entire signal and know what we should expect to see. That does take work. There has been hybridization work going on for decades, but there's still more to be done, especially hybridizing NR with self-force, which I think is a really promising area. But it's definitely stuff we need to continue to explore, and we need to continue to assess how accurate we need those hybridizations to be, and exactly at what point should the NR end and should the other methods begin. We just need to continue to explore that and establish as we move forward. All right, so then there's also the issues of numerical error. So I commented that there's no missing physics and our only limitations are computational in nature. Well, here's those computational in nature issues. So first off, we're performing our simulations on finite grids, and therefore we have finite grid resolution. Now, we know that our codes converge as we increase resolution, but just by the purely computational nature, you also know that your highest resolution is still not perfect. It's not ground truth. It's not infinite resolution. So these two plots over here address this issue. This top one is a nice plot out of Purer and Haster. That paper talks a lot about errors associated with models, particularly for 3G ground-based, but it also addresses the uncertainty that you get in numerical relativity waveforms by comparing two SXS resolutions and estimating the error between those, and you get this mismatch. And then these diagonal lines are saying, as a function of SNR, what mismatch do you need below what mismatch do you need in order to not bias your results? And as you can see, as you increase in SNR, this mismatch jumps above our necessary mismatch. And so that means that we need to improve. We need to improve our mismatches. And then similarly, a plot from a paper of mine exploring the same concept, but now very specifically for numerical relativity, and trying to actually understand the error in our highest resolution waveform as compared to infinity. Here, again with the SNR on the x-axis, and now on the y-axis is what specific grid resolution you would need in a finite differencing code in order to produce a waveform that is indistinguishable from an infinite resolution waveform. And this horizontal line is a little less applicable now than when this paper came out, because it's M by 400, which at the time was our highest resolution in our public waveform catalog. We've now gone higher, but it still does work as a rough idea of what's doable / easy, whereas things above it are going to be harder, and they're going to take longer, and it's not going to be very practical to fill in a catalog of simulations with higher resolutions with current codes. Okay, so here, the three different lines. The blue is an equal mass system. You can see that even at the SNRs of 3,000 that Lisa might see, we still don't need that high of resolution. Great, something's on track. But with mass ratio equals 6, you start to jump up above it around SNR 1,000, and that was face on. Now when we add on inclination, which means that you're seeing higher order modes more frequently or more apparently, this becomes more significant even sooner. So this is definitely something that we're going to want to tackle moving forward. Then, in addition to the fact that we are on finite grid resolutions, we're also on finite grids. We are really far away from the binary black holes that we're going to watch merge, but we can't perform a simulation on that large of a grid. So typically what we do is we extract on finite resolution radii and then extrapolate to what that would look like at spatial and temporal infinity. And that introduces its own errors. There are better methods that people are working on and developing and have put a lot of effort into in the recent years, such as Cauchy characteristic evolution, that can help minimize these errors. So a lot of codes are moving that direction, and that should help tackle this well. All right, so now, do these errors actually matter? And this is very related to the talk Martin gave as well, because he mentions, I think, all of these three things there as when talking about waveform accuracy needs. But in this plot, we show as a function of mass and redshift/distance what SNRs Lisa might see. And so this is where I got that number 3,000 that I said earlier. We could hit SNRs up to and beyond 3,000. And for reference, if that number doesn't mean much to people, last I checked, the highest SNR in LIGO was like 32-ish. So this is orders of magnitude higher. And so this can cause a number of problems. One of the first things we want to know is, will it bias our parameter estimation? So I hope some of you were able to go to Awesome John's talk on Monday, where he talked specifically about whether these errors could bias parameter estimation. And this plot is straight out of a paper that I have with him that I think was actually officially published yesterday, so that's always exciting. All right, so I don't think everyone in this room is probably familiar with corner plots, so let me just give you a quick rundown on what you're looking at here. So this is used in parameter estimation when you get a signal, or when, in this case, you inject a fake signal, and you want to see what were the parameters of the system that led to that signal. So here, we're trying to recover the chirp mass, which is a type of measure of total mass, the mass ratio, and chi-effective, the effective spin aligned with the orbital angular momentum. And if we start with the diagonals, these are your posteriors that essentially show what you think that mass probably was and how certain you are about it, what your 90% confidence interval would be, et cetera. And then if we look on the off diagonals, now you've got two-dimensional posteriors where you have the contours are the 90% confidence intervals. Okay. So what this plot is actually showing in relation to this is we injected numerical relativity simulations of different resolutions to see how different they actually look in terms of parameter estimation. And you do, in fact, at an SNR of 203, for some of these, you actually do see a significant shift. And so here's the thing. That bias is going to be there no matter what. But as your SNR gets louder, you're going to get a narrower and narrower posterior. And you're going to get more and more and more confident in your result, to the point that your systematic biases might overpower your statistical biases. And that would mean that our numerical relativity would be holding us back. And that's not what we want. That's definitely not what we want. Now, if you actually look at these values, though, it's not like if you look at this x-axis, this isn't a huge shift. And these are comparing some low resolutions to our high resolutions. So there is a shift that is measurable, but now what we need to understand is, well, how well do we actually need these measurements to be to not be affecting things like our astrophysical interpretations of this data? And so that's the next step on understanding this. Okay, so in addition to biasing parameter estimation, we could also imitate or hide beyond GR effects. And so that's, one of the most exciting things about having a detector like this is your ability to do precision tests of gravity. So we want to make sure that we're not the reason we can't do that. And similarly, we could also contaminate quieter signals in this global fit that we're also excited about. And so here is just a quick plot also from the LISA Waveform Working Group white paper about what residuals you might leave behind if you mismodel a loud signal. So this is an SNR about 1,000. The black line is a high resolution waveform. The blue line is a low resolution waveform. Or the blue line here, sorry. And then this blue line is the residual when you subtract those out. And you can see that that residual is above the noise curve, which roughly means it's detectable. It's having some sort of appreciable impact. And it actually looks similar to this other residual that I won't go into detail with, but you could essentially treat that other residual as missing physics. And you can notice that this looks remarkably similar. And so not only might we be contaminating other signals, but we might actually be missing physics if we use too low resolution numerical relativity waveforms. A little less doom and gloom, though, is this plot on the right, which is a more typical signal, SNR 200. It's still above the noise curve, but not as bad. So, but for the golden ones that we're so excited about, we're definitely going to need to continue to make progress. All right, so just to bring that all back together and summarize what we've just been saying, Numerical relativity is facing some challenges moving forward. We're doing a good job tackling them, and I'm really optimistic about the way we're moving, but we're going to need to focus on things like our parameter space coverage of high mass ratios, high spins, especially processing spins, eccentricity, matter beyond GR. We need to think about our waveform quality in terms of length and finite differencing and waveform extraction. And then I didn't actually say this one yet, but I repeatedly said how things were computationally expensive. So in order to actually accomplish this in the next 10 years, we need codes that scale more efficiently as well. Now, what is exciting is that people are already working on this. There are already next-generation numerical relativity codes, such as Carpet X, which is the evolution of the Einstein toolkit, Spectre, which is the next generation out of the SXS collaboration. We've got Black Holes at Home, which is doing incredibly efficient simulations, Sphinx BSSN, which is diving into GRMHD, and much more. That's just a handful of them. So this is something that people are passionate about, and we are making lots of progress on. So I'll leave you on that much more optimistic note, just to state that numerical relativity is the backbone of our ability to study the merger of binary black hole systems, at least of comparable mass. And in order to do that, LISA is going to require us to have template banks that are vast and are high quality. And in order to accomplish that, we need codes that are able to produce highly accurate and highly efficient numerical relativity simulations. All right, thank you.
I see some questions. I saw Tyson in the back there.
For your tests where you were showing residuals, if you use lower resolution waveforms than showing the power spectra, were those lower resolution waveforms allowed to fit the injection, or were they force-fed using the same parameters?
Yeah, excellent question. Do I need to repeat the question, or can people online hear? I guess with the microphone, we're probably all right. Okay, anywho, yes, for those, it was specifically the exact same parameters, which is not the most accurate way to do this in terms of thinking about whether you're going to contaminate the data, because I did mention that you can bias your parameter estimation, so the thing that actually best fits it is going to be a little shifted, and hopefully you'll get significantly less residuals. That's definitely another step to this project that we'll need to do.
I think there was another question on the middle row here.
This is more of a curiosity question. In recent years, there were some algorithms being proposed on how to solve PDEs on quantum computers, which I think have polynomial or even exponential speedup. And okay, obviously the hardware is not available today, but maybe in 5 to 10 years. And I was just wondering whether there are people looking into that.
I have not heard much in terms of what's actually going on with quantum computers in this world. So I can't answer really specifically what would actually be happening there, but I definitely know that people are trying to tackle ways to make more efficient codes that will scale more efficiently. So I think a lot of people would definitely be open to exploring that and utilizing that with numerical relativity in order to, be able to scale so much faster and produce simulations much quicker would be great. I hope people are leaning into exploring that for sure.
Looks like we have a question over here.
Yes, thank you for your nice talk. I have a question. What is the impact of testing the GR when we assume that we have Gaussian noise when we analyze the data?
Yeah, so there's definitely still a lot of work that needs to be done on understanding how well we will be able to test beyond GR. I will point to there have been a lot of talks in the fundamental physics area during this conference about our ability to test beyond GR theories with LISA data. I haven't really dove into that much yet, so I can't answer anything specifically. What I've been really interested in is whether any of our systematic errors relating to the waveforms themselves could affect our ability to test beyond GR, and so that's something that we're definitely wanting to explore. But I mean, yeah, with systematic errors and with statistical errors, it's definitely going to be challenging, but I think it's a big opportunity that hopefully we'll be able to tackle.
And then one final question here.
All right, thank you so much for your talk. It's a question about not so distant future, 2035. So, if you remember, Katie was discussing in the morning these systems that Lisa will observe, black hole binaries that are going to emerge in like 5-10 years. So the question is the following. Will it be practically useful to make specific template banks dedicated or based on the measurements of Lisa so that the detection by LIGO will be better? Is it practically useful?
That could be interesting, because, well, one of the things about numerical relativity is while it can be computationally intensive to produce full catalogs, sometimes it's nice when you can just do a targeted simulation at super high resolution for a specific waveform. Now, what I will say is, oh, well, actually, no, because next generation ground-based detectors will also have really high signal-to-noise ratios. So we're going to face a similar challenge. And so, yeah, I think it would actually be really great to be able to know ahead of time from Lisa, hey, let's run a suite of simulations near this point with really high resolutions and see how well we can analyze it. I think that would be a great idea and could be a really useful opportunity.
Thank you.
All right, let's thank Deborah again.